If we look at the history of science, we'll notice a highly curious pattern. Almost every great discovery initially met not with applause, but with a blank wall of misunderstanding. We're used to thinking that science is a crystal clear, objective process where facts are instantly recognized as truth. But in reality, the scientific world is incredibly conservative. Why do professors spend years ignoring evidence lying right in front of their eyes? And why is it that people from completely different fields often notice what recognized experts miss? Today, we're going to walk through 12 concepts that initially triggered nothing but patronizing smiles. We'll break down in detail how these unbelievable guesses fought their way through and became the foundation of our modern world. Let's mentally travel back to the late 19th and very early 20th century. Geology back then was a solid, calm, and, if you could call it that, motionless science. The learned men of the time were absolutely certain of one undeniable fact. The solid earth beneath our feet is static. Continents and oceans had been in their places since the creation of the world, as if they were nailed dead to the ocean floor with giant nails. Sure, geologists saw mountains, saw deep gorges, and understood that the terrain changes. But how did they explain it? At the time, the so-called contraction hypothesis ruled the day. The core of it was extremely simple and in its own way, logical. Imagine an apple left on a table. Over time, it dries out, loses moisture, and its smooth skin gets covered in deep wrinkles. Scientists believed the Earth was exactly that kind of cooling cosmic apple. It used to be a blazing hot sphere, and then, over hundreds of millions of years, it began to cool. As it cooled, its volume shrank, and the solid Earth's crust was forced to contract, forming giant folds. We call these folds mountain ranges, and the dips between them filled with water, forming oceans. It all sounded neat and beautiful, but this theory had gaping, colossal holes in it. The main problem was paleontology. Scientists kept finding fossils of absolutely identical ancient animals and plants on continents separated by thousands of miles of impassable saltwater. For instance, the remains of the ancient freshwater reptile Mesosaurus were found in both South America and South Africa. But a freshwater reptile physically couldn't swim across the Atlantic Ocean. To save their old theory, geologists came up with unbelievable things. They claimed that in the distant past, giant land bridges existed between the continents, colossal strips of land that animals walked back and forth on, and then these bridges sank without a trace into the depths of the ocean. And onto this stage steps a man named Alfred Wegener. It's important to note one critical detail. He wasn't a geologist at all. He was a meteorologist, an atmospheric researcher, and a brave polar explorer who set records flying hot air balloons and led grueling expeditions in the harsh ice of Greenland. In 1910, looking at a geographical map of the world, Wegener noticed something many had seen but no one had taken seriously. The coastlines of eastern South America and western Africa fit together like two pieces of a torn puzzle. The bulge of Brazil fit perfectly into the dent of the Gulf of Guinea. Anyone else would have just smiled at this funny coincidence, but Wegener approached the issue with the meticulousness of an observational scientist. He decided to test it. What if this isn't a coincidence? Wegener began meticulously gathering data. He studied the geological layers on both coasts of the Atlantic and found that ancient rock formations in Brazil were absolutely identical to rocks in Africa. Furthermore, Coal seams in Europe continued perfectly into North America, as if someone had torn a single book in two. He found traces of ancient glaciers in the tropical forests of India and equatorial Africa. To a meteorologist, this was obvious nonsense. Glaciers couldn't form on the equator. Therefore, India and Africa must have once been somewhere completely different, much closer to the South Pole. In 1912, Alfred Wegener gives a public lecture, and in 1915, he publishes an epoch-making book. In it, he puts forward an idea that was completely insane for the time. He declares that no sunken land bridges ever existed. Instead, about 250 million years ago, all the land on the planet was gathered into one giant supercontinent, which he named Pangaea, meaning all Earth in Greek. And then, for some unknown reason, this supercontinent fractured, and its pieces slowly began to drift apart in different directions, like giant ice flows on the surface of a pond. This is the concept of continental drift. You'd think the evidence was obvious. Matching coasts, identical geological layers, identical fossils, weird climate footprints. But how did the scientific community react? They went into an indescribable rage. Wegener was subjected to a real intellectual flogging. His idea was called pseudo-scientific nonsense, an amateur's fantasy, and a fairy tale for children. Respected geologists wrote scathing articles claiming that a man without a specialized geology degree had no right sticking his nose into their science with his ridiculous fantasies. But why were the academics so cruel? The thing is, Wegener's theory had one fatal flaw. He couldn't explain the mechanism. He couldn't answer the biggest question. Exactly what force is capable of moving entire continents through the solid ocean floor? Wegener guessed it might be caused by centrifugal force from the Earth's rotation or the tidal pull of the moon. But physicists quickly grabbed their pencils and paper, ran the numbers, and destroyed these arguments. They proved that the moon's tidal forces are millions of times too weak to move continents. And if such a force actually existed, it would stop the Earth from spinning in just a few years. Wegener found himself in a tragic situation. He saw the aftermath of the process. He gathered an incredible amount of circumstantial evidence, but he couldn't demonstrate the engine of this colossal machine. Because of this, the scientific world slammed its doors in his face. In 1930, Alfred Wegener set off on another expedition to Greenland to resupply a remote weather station. On the way back, during the polar night and at minus 50 degrees, his heart gave out. He died absolutely certain he was right, but remaining an outcast in the eyes of the global scientific community. He was buried right there in the ice, and over time, his body, frozen into the glacier, began its own slow drift toward the ocean. Decades passed. The second half of the 20th century arrived. During World War II, military engineers created sonar to hunt for enemy submarines. When the war ended, these devices started being used for scientific purposes to study the ocean floor. Up until that moment, people thought the ocean floor was a flat, boring plain covered in mud. In the 1950s, cartographers Marie Tharp and Bruce Heezen began mapping the Atlantic Ocean floor in detail, based on sonar data. And what they found was a total shock. Right in the middle of the Atlantic, mirroring the outlines of the coastlines, stretched a colossal underwater mountain range. It was named the Mid-Atlantic Ridge. Later, it turned out that these kinds of ridges wrap around the entire globe like the seams on a baseball and their total length is over 65,000 kilometers. But the most interesting part was hiding right down the center of these underwater mountains. A deep cleft ran through it, a so-called rift valley. It looked like the ocean floor had been literally torn open down the middle. That's when the puzzle started coming together. It turned out our planet's crust isn't a single solid shell. It's broken into several giant chunks, which we now call tectonic plates. And these plates really are constantly moving. But the engine driving this process isn't lunar tides, like Wegener thought, but thermal convection inside the Earth itself. Let's break this down a bit more. Picture a thick pureed soup slowly boiling on the stove. At the bottom of the pot, the soup heats up from the fire, gets lighter, and rises to the top. Once it reaches the surface, it cools down a bit, gets denser and heavier, and then sinks back to the bottom. This circulation of liquid is called convection. The exact same process is happening deep within the bowels of our planet. The Earth's core is blazing hot, sitting at around 6,000 degrees. This is partly leftover heat from when the planet formed, and partly the result of the continuous decay of radioactive elements: uranium, thorium, and potassium. This colossal heat warms the mantle, a thick layer of viscous rock. The blazing mantle slowly rises to the surface. Where it reaches the Earth's crust, like under the mid-ocean ridges, it literally pushes the tectonic plates apart, filling the forming cracks with fresh lava. The plates slide away, carrying entire continents on their backs. And at the opposite end of the plate, where it crashes into another plate, the heavy, cold, oceanic crust dives under the continent and sinks back into the blazing mantle to melt. It's a giant, non-stop conveyor belt. The final, ironclad proof of the plate tectonics theory was the phenomenon of paleomagnetism. The Earth has its own magnetic field. But this field isn't permanent. Every few 100,000 years, the planet's magnetic poles flip. The North Pole becomes the South Pole, and vice versa. When liquid magma spills out of cracks in the ocean floor, it contains iron particles. While the magma is liquid, these particles act like tiny compass needles. They align themselves strictly along the Earth's magnetic field lines. And when the magma solidifies, turning into solid basalt, these magnetic needles get permanently locked into the rock. When research ships started towing magnetometers over the ocean floor, they saw a fantastical picture. The ocean floor was striped. Stripes with normal magnetization alternated with stripes of reverse magnetization. And most importantly, this zebra stripe pattern was absolutely symmetrical on both sides of the underwater ridge. It acted like a giant natural tape recorder that had been recording the seafloor spreading process for millions of years. New rocks popped up in the center, got magnetized by the current Earth's field, and slowly crawled to the sides, making room for a fresh batch of magma. Today, thanks to global navigation satellite systems, we can measure the movement of the continents in real time down to the millimeter. We know for a fact that North America and Europe are drifting apart at a speed of about 2.5 centimeters a year, which, by the way, is roughly the same speed our fingernails grow. Alfred Wegener was absolutely right. The continents really are dancing their incredibly slow but non-stop dance on the surface of the viscous mantle. They crash together, crumpling their edges into giant mountain ranges like the Himalayas, and pull apart, opening up new oceans. The entire history of our planet is the history of a constantly redrawn geographical map. This story shows us something fundamentally important about the nature of scientific discovery. Sometimes, to see the truth, you have to step outside your narrow specialization. You have to look at the problem with fresh eyes, without being chained by the authority of old theories. Wegener's ideas were considered scientific heresy for half a century. He was mocked by the very people who wrote the textbooks. But nature doesn't care about academic titles. If the facts show that massive chunks of land are floating across the planet, then that's exactly what's happening. Even if we don't yet understand exactly how the engine of this colossal raft works. The ground beneath our feet turned out to be not a dead, static rock, but a living, breathing, constantly changing machine. And this realization forever changed our place in this world. Let's mentally travel to mid-19th century Europe to truly grasp the scale of the story we're about to unpack. We need to throw out absolutely everything we know about modern medicine. Forget about sterile white wards, disposable gloves, UV lights, and antibiotics. A hospital back then was a completely different, terrifying place. In those years, surgeons operated in their normal, everyday frock coats. If dried blood or stains from previous surgeries were left on the fabric, it wasn't considered dirt. On the contrary, an apron stiffened by time was seen as a badge of honor, a symbol of the doctor's colossal experience and skill. After using their instruments, they might just wipe them with a dry rag and put them back in a velvet case. It never crossed anyone's mind to boil them. Why? Because the academic science of the time had a completely different understanding of how diseases started. Medical universities were completely dominated by the miasma theory. The learned men seriously believed that infections were spread through bad air. It was thought that rotten organic matter released invisible, poisonous vapors, miasmas. If a person breathed in this air, the balance of humors in their body was thrown off, and they got sick. No microbes, bacteria, or viruses existed in the worldview of a respected medical professor. The idea that tiny, invisible creatures could kill a grown adult sounded like a children's fairy tale, unworthy of a serious researcher's attention. It was exactly in this intellectual atmosphere, in 1846, that a young Hungarian doctor named Ignaz Semmelweis got a job as an assistant at the Vienna General Hospital. This was one of the largest and most modern medical facilities in all of Europe. Semmelweis was assigned to work in the maternity ward, which consisted of 2 independent clinics, and what he encountered there forever changed the course of medical history. An epidemic of childbed fever was raging through the hospital. This is a horrific disease that we now call postpartum sepsis. Women who checked into the clinic perfectly healthy would, a few days after giving birth, start suffering from a high fever and soon die in unbearable agony. But the weirdest part was hidden in the dry, ruthless statistics. The first clinic, where medical students practiced and degreed doctors worked, had catastrophic mortality rates. In some months, 1 in 6 mothers died there. The mortality rate hovered steadily around 16%, and sometimes spiked to a mind-boggling 30%. The second clinic, located literally in the next wing of the same building, was used for training midwives. There, the mortality rate was only about 2%. The difference was so colossal and obvious that the whole city knew about it. Women would beg in tears not to be sent to the first clinic. They would fall to their knees before the doctors, preferring to give birth right out on the street, because the survival rate of street births was way better than in the wards run by the capital's best professors. Ignaz Semmelweis had a deeply analytical mind. He couldn't just accept the idea that women were dying due to an evil fate or bad air. If the problem was miasmas, then both clinics, sharing the same roof and breathing the same air, would have had the same mortality rates. Semmelweis started acting like a real detective. He decided to use a strict method of eliminating variables. First, he guessed the problem was the body position during birth. In the first clinic, women delivered lying on their backs, and in the second, lying on their sides. Semmelweis made the doctors in the first clinic deliver babies with women on their sides. The mortality rate didn't budge a fraction of a percent. Then he looked at the psychological factor. Every time someone was on their deathbed in the first clinic, a priest would walk through the wards to administer the last rites. The clergyman walked slowly, and his assistant rang a bell. Semmelweis thought this ringing struck mortal terror into the mothers in labor, draining their life force. He convinced the priest to change his route and come in silence, without the bell. The result was 0 again. The mothers kept dying. Semmelweis checked the food quality, the ventilation, the cleanliness of the bed linens. Everything was absolutely identical in both clinics. The only difference left was the staff. The answer came suddenly, bringing a personal tragedy with it. In 1847, Semmelweis's close friend, forensic medicine professor Jakob Kolečka, was performing an autopsy in the morgue. During the procedure, a clumsy student accidentally pricked the professor's hand with a scalpel, leaving a small cut. A few days later, Kolečka died. The symptoms of his illness were chillingly familiar to Semmelweis. When he looked at his friend's autopsy results, he was stunned. The internal tissue damage, inflammation, and pus were absolutely identical to what he saw every day in the dead mothers. In that moment, a breakthrough happened in Semmelweis's mind. He pieced the scattered facts together into one terrifying picture. Every morning, the doctors and students of the first clinic started their day in the anatomical theater. They performed autopsies on dead patients to study pathology. Then, wiping their hands on a rag, they went straight to the maternity ward to examine pregnant women. The midwives from the second clinic never visited the morgue and never touched dead bodies. Semmelweis drew a conclusion that flipped his world upside down. The students and doctors were literally carrying death on their hands. He called these cadaverous particles. Let's break this down using a simple mental analogy to understand the mechanics. Imagine your fingers are covered in thick, sticky paint that is invisible to the human eye. You grab a door handle, flip through a book, shake hands with a coworker, and then examine a patient. Everywhere your skin touches a surface, a tiny, invisible smear of this substance is left behind. Regular water doesn't wash this paint off. Even a bar of standard soap just smears it around your palms a bit. To completely clean your skin, you'd need a powerful chemical solvent. That is exactly how disease-causing microorganisms work. But the depth of the problem was that in the mid-19th century, nobody on the planet knew bacteria existed. Semmelweis didn't see germs under a microscope. He just deduced their presence using ironclad logic and statistics. To destroy these hypothetical cadaverous particles, Semmelweis proposed a radical solution. Since the particles came from corpses, they had a distinct putrid smell. Semmelweis decided he needed to use a substance capable of completely destroying that smell on the skin. His choice fell on a solution of chlorinated lime. He issued the strictest order. Every doctor, every student before examining a mother in labor must thoroughly wash their hands in the chlorinated lime solution until their skin stopped smelling like the morgue. Also, instruments had to be soaked in this solution. The results were phenomenal. In just a few months, the mortality rate in the first clinic plummeted from 18% to an astonishing 1% or so. And in some months of 1848, Not a single woman died in Semmelweis's ward. It was an absolute, unconditional triumph of the scientific method. The problem was solved. You'd think the medical community would carry Semmelweis on their shoulders, shower him with awards, and immediately implement his method in all the hospitals across Europe. However, what actually happened was something completely different. Semmelweis's discovery hit a blank, monolithic wall of furious resistance. To understand the reason for this reaction, we need to dive into the psychology of the academic community of the time. Medical professors were the elite of society. They were respected gentlemen from the upper class. And suddenly, some young upstart from Hungary tells them that they, the respected lifesavers, are actually filthy murderers. He tells them that their unwashed hands are the reason thousands of young mothers died in agony. It's a classic example of cognitive dissonance. The human psyche has powerful defense mechanisms. To admit Semmelweis was right would mean taking on a colossal burden of guilt for past deaths. For many prominent doctors, this was psychologically unbearable. It was much easier to declare Semmelweis a crazy fantasist. Authoritative obstetricians publicly mocked his theory. The prominent American doctor Charles Meigs openly stated that a gentleman's hands were inherently incapable of transmitting disease. Doctors refused to wash their hands in chlorinated lime, complaining the solution dried out their skin and caused irritation. They sabotaged orders, deliberately ignored the procedures, and then noted with satisfaction when the mortality rate started climbing again. Semmelweis was accused of faking his statistics. Eventually, the management of the Vienna hospital simply didn't renew his contract. The man who figured out how to save tens of thousands of lives every year was thrown out on the street. Semmelweis returned to his native Budapest, where he tried to implement his methods at the local St. Rochus hospital. And there, too, the mortality rate plummeted to minimal levels. He wrote desperate letters to the leading doctors of Europe, calling them irresponsible murderers, begging them to come to their senses. But all he got in return was disdainful silence. The scientific world shut its doors on him. Gradually, despair turned into severe depression and a nervous breakdown. Semmelweis's behavior became increasingly erratic. He would stop random strangers on the street to tell them about the need to wash hands before childbirth. In 1865, colleagues and relatives tricked him into going to an insane asylum. When he realized where they brought him and tried to leave, the orderlies beat him brutally. During this struggle, Semmelweis got a wound on his hand. The wound got infected, leading to blood poisoning. Ignaz Semmelweis died of sepsis, the exact same disease whose nature he had unraveled, and which he had spent his life trying to save others from. He was only 47 years old. Justice didn't prevail until decades later. At the end of the 19th century, the brilliant French chemist Louis Pasteur ran a series of elegant experiments and proved that fermentation and rotting were caused by invisible microorganisms. He definitively disproved the theory of spontaneous generation and miasmas. Following him, the German microbiologist Robert Koch developed strict rules to link a specific bacterium to a specific disease. Science finally got the tools to see the invisible. Under the lenses of powerful microscopes, scientists discovered the Streptococcus bacteria, that very invisible killer, that very cadaverous particle Semmelweis had tried to wash off with chlorinated lime. The germ theory of disease became an undeniable fact, the foundation of all modern medicine. Surgery moved into sterile operating rooms, doctors put on rubber gloves, and hand washing became a basic hygiene rule for every civilized human. The story of Ignaz Semmelweis isn't just a tale of a medical discovery. It is a deeply philosophical parable about the nature of scientific discovery and the blindness of human pride. Semmelweis made a mistake that society rarely forgives. He was right too early. He didn't have the theoretical framework to explain why his method worked. He only had facts, statistics, and saved lives. But for an academic world stuck in old dogmas, that wasn't enough. Today, Ignaz Semmelweis's name is written in gold letters in the history of science. He is called the savior of mothers. In psychology and the philosophy of science, there is even a specific term, the Semmelweis reflex. It means the automatic, immediate rejection of new knowledge or discoveries, simply because they contradict established norms and paradigms. This story makes us stop and think about an important question. How often do we ourselves turn away from obvious truths just because they disrupt our comfortable way of thinking? How often do we prefer to believe in familiar misconceptions, refusing to admit obvious facts? The invisible killers the Hungarian doctor found weren't just on surgeons' hands. The most dangerous things turned out to be the invisible barriers in the minds of people who thought they held the absolute truth. Let's pause for a moment and look at the night sky. When we look up at the stars, it feels like we're looking at something unshakable, eternal, and absolutely motionless. This is exactly how all of humanity viewed the cosmos for millennia. In the early 20th century, the scientific community was monolithic in its belief. The universe is infinite in space and eternal in time. It never had a beginning, and it will never end. This concept of a static universe wasn't just a convenient physics model. It was a profound philosophical foundation. An eternal universe felt aesthetically perfect. It didn't need a moment of creation, which meant science could elegantly sidestep any tough questions about what happened before the beginning of time. The cosmos was seen as a giant, perfectly tuned stage where stars are born and die, but the structure of the stage itself never changes. In 1915, Albert Einstein publishes his general theory of relativity. It was a colossal breakthrough that changed the rules of the game forever. Einstein proved that gravity isn't some invisible thread pulling objects together. Gravity is the curving of the very fabric of space and time. Let's break this down a bit more. Imagine a tightly stretched elastic trampoline mat. If you place a heavy bowling ball in the center, it will warp the fabric, creating a deep funnel. If you now roll a glass marble along the edge of the trampoline, it will start spiraling down into this funnel, following the curve of the surface. In the exact same way, massive objects like the sun curve the space around them, forcing planets to move in orbits. But there was an incredibly weird catch hiding in this. When Einstein applied his brilliant new equations to the universe as a whole, the math spit out a catastrophic result. If all stars and galaxies have mass, they must inevitably attract each other. Gravity is a force that only pulls. Therefore, a static universe simply cannot exist. Under the influence of its own colossal mass, it would have to start contracting and eventually collapse into a single point with a crunch. However, astronomers of the time didn't see any collapsing happening. The stars hung in their places. To save the static model and make the equations fit the generally accepted worldview, Einstein inserted a special mathematical crutch into his calculations. He called it the cosmological constant. Essentially, it was a hypothetical anti-gravity force inherent to the vacuum itself, which pushed objects apart over vast distances, perfectly balancing out their gravitational pull. The universe was saved, the equations balanced. Einstein relaxed. But the problem is that artificial constructs in physics rarely last long. In 1927, a man with a totally unique background steps into the scientific arena. His name was Georges Lemaitre. He was a Belgian astrophysicist, a physics professor, and, most surprisingly, an ordained Catholic priest. This dual identity played a huge role in how the world received his discoveries. Lemaitre studied the equations of general relativity in detail and concluded that Einstein's cosmological constant made the system highly unstable. It was like trying to balance a pencil on its tip. The slightest nudge, and the balance is ruined. Lemaitre took a pencil, crossed the cosmological constant out of the equations, and looked at what happened. The math gave a clear, unambiguous answer. The universe is not at rest. It must either be contracting or expanding. Relying on early astronomical observations, Lemaitre drew a counterintuitive conclusion. The space of our world is currently expanding rapidly in all directions. But what does that mean then? If the cosmos is getting bigger every second, it's logical to assume it was smaller in the past. Lemaitre proposed a thought experiment. Let's run the tape of time backward. Yesterday, the universe was a little denser than today. 1,000,000 years ago, galaxies were much closer together. And if we rewind time billions of years, we'll reach a point where all matter, all energy, all light, and space itself were crushed into one tiny, unimaginably dense and hot dot. Lemaitre called this dot the primeval atom. He declared that time and space themselves began their existence the moment this primeval atom became unstable and decayed. To really grasp this concept, we have to ditch our usual earthly thinking. When we hear the word explosion, we picture dynamite exploding in an empty room, where shrapnel flies from the center to the walls. But the expansion of the universe works differently. Outside the primeval atom, there was no empty room. There was no external space for matter to expand into. Space itself was born in that moment. Imagine the surface of a regular balloon on which you've drawn a bunch of little dots with a marker. These dots are galaxies. Now start blowing up the balloon. You'll notice the dots don't move across the rubber itself. The rubber itself stretches, increasing the distance between the dots. Meanwhile, every dot sees all the other dots moving away from it. In this model, there is no center of expansion and no edge. The fabric of reality itself is expanding. When Georges Lemaitre presented his hypothesis to the scientific community, the reaction was more than chilly. It was downright hostile. Albert Einstein, after reviewing the Belgian scientist's calculations, delivered a famous quote that basically meant, "Your math is flawless, but your grasp of physics is abominable." Why did the intellectual elite of the time reject this idea so fiercely? It's a pretty heavy story. The main problem wasn't physics, but psychology and prejudice. Lemaitre's colleagues couldn't get past his priest's collar. They suspected Lemaitre was trying to smuggle religion into astrophysics. The idea that the universe had a starting point, a birthday, a starting line, sounded way too much like the biblical story of creation out of nothing. Many respected scientists saw this as disguised creationism, a clumsy attempt to use complex math to prove the existence of a divine creator. One of the most hardcore critics of Lemaitre's concept was the brilliant British astrophysicist Fred Hoyle. Hoyle was a devout supporter of the steady-state theory. He believed that as galaxies moved apart, new matter spontaneously popped into existence in the empty pockets of space, keeping the density of the universe constant. In 1949, speaking on a popular science radio show, Hoyle decided to publicly mock Lemaitre's idea. Trying to show the absurdity of the thought that the entire cosmos could pop out of a single dot, he dismissively called the theory the Big Bang. Hoyle meant it as an insult, a cartoonish term to shut down the debate. But ironically, that snappy name stuck in science forever. Nevertheless, science isn't an argument over tastes. It's a search for objective proof. And that proof soon arrived. In 1929, American astronomer Edwin Hubble, working on the giant telescope at the Mount Wilson Observatory, made a stunning discovery. He was analyzing the light coming from distant nebulas, which turned out to be separate galaxies. Hubble used the Doppler effect. To understand its mechanics, remember the sound of a passing ambulance. When the ambulance is rushing straight at you, the sound waves compress, and the siren sounds high and piercing. But the second the vehicle passes by and starts driving away, the sound waves stretch out, and the siren's pitch drops sharply, becoming low and muffled. Light waves behave exactly the same way. If a light source is rapidly approaching the observer, the light waves compress, and the light shifts to the blue part of the spectrum. But if the source is moving away, the waves stretch out, and the light turns red. Physicists call this phenomenon cosmological redshift. Hubble found that the light from the vast majority of galaxies is shifted toward the red. Furthermore, he derived a strict rule. The further away a galaxy is, the redder its light gets, which means the faster it is flying away from us. This was a triumphant observational confirmation of what Lemaitre's calculations had predicted. The fabric of the cosmos really was stretching in all directions. Despite Hubble's data, the debates between Big Bang supporters and steady-state fans raged on for a few more decades. Scientists needed a final, irrefutable piece of evidence, and they found it totally by accident. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs. They had a giant horn antenna at their disposal, originally built for satellite communications. The scientists wanted to use this ultra-sensitive instrument to map the Milky Way galaxy in radio waves. But right after turning the gear on, they hit an insurmountable roadblock. The antenna was picking up a constant, annoying background noise. It was a low-frequency microwave hiss that didn't go away day or night. The noise was absolutely uniform, no matter where the scientists pointed the huge horn, at the sun, at empty patches of sky, or at the center of the galaxy. Penzias and Wilson spent months trying to find the source of the interference. They checked cables, re-soldered contacts. They even looked at the pigeons that had built nests inside the giant horn. The scientists grabbed brushes and thoroughly scrubbed the bird droppings off the inside of the instrument, thinking the organic deposits might be causing electrical interference. But when they turned the gear back on, the mysterious hiss hadn't gone anywhere. It was spilled all over the sky. The answer turned out to be grander than anyone expected. Around the same time, a group of theoretical physicists at Princeton University was calculating what the universe should look like if the Big Bang theory were true. They concluded that if the cosmos really started from a state of incredibly dense and hot plasma, that primordial heat couldn't have just disappeared. As space expanded, this radiation should have cooled and stretched out. Billions of years later, it should have turned into a cold ocean of microwaves, filling every cubic centimeter of the vacuum. The temperature of this hypothetical leftover heat, according to the calculations, was supposed to be about 3 degrees above absolute zero. Penzias and Wilson had recorded a noise matching a temperature of 2.7 degrees above absolute zero. They had completely accidentally caught the echo of creation. They heard the whisper of the cooling primeval atom. This discovery, for which the scientists later won the Nobel Prize, put a final period on the great debate. The cosmic microwave background radiation became the undeniable proof that forced the academic world to surrender unconditionally. The steady-state theory crumbled to dust, and the Big Bang concept became the unshakable foundation of all modern cosmology. Georges Lemaitre lived to see the triumph of his idea. He died in 1966, having learned that the relic radiation predicted by his calculations had indeed been found. The priest astronomer, who was mocked by the greatest minds of his era, turned out to be right. Today, thanks to space telescopes and ultra-precise measurements, we know the age of our world with incredible accuracy. Our universe has been expanding for 13.8 billion years. All the matter that makes up our bodies, our planet, and distant stars was once crushed into an infinitely small volume. We are literally the cooled down sparks of that very first firework that once kick-started the flow of time. But the finale of this story leaves us facing an even greater mystery. The Big Bang Theory does a beautiful job describing the evolution of the universe from the first fractions of a second of its expansion. But it doesn't answer what caused the primeval atom to lose stability. Moreover, we are only capable of observing the part of the cosmos whose light has had time to reach us over billions of years. This is our observable horizon. I wonder what's hiding beyond that boundary. Does the endless sea of galaxies continue out there? Or do completely different laws of physics rule there? Laws we have yet to discover. Let's mentally jump back to the 19th century, to the moment Charles Darwin published his masterwork on the origin of species. The classic theory of evolution gave humanity an incredibly neat and logical picture of how life developed. At the core of this picture lay two fundamental principles: random mutations and ruthless natural selection. Evolution was viewed as an endless, brutal gladiator arena where only the strongest survive. Every new biological species, every new physical trait, whether it was a giraffe's long neck or an eagle's sharp eye, was seen strictly as the result of countless tiny changes that piled up over millions of years amid fierce competition for resources. Nature was seen as a non-stop battlefield. This paradigm of competition took such deep root in the scientific mind that it became absolute dogma. Scientists looked for answers to all biological mysteries strictly through the lens of slow, gradual improvements and rivalry. But in the mid-20th century, when researchers got their hands on powerful electron microscopes, they hit a mystery that the theory of slow mutations simply couldn't explain. The problem lay in the fundamental structure of living things. Biologists discovered that all life on our planet is clearly split into two totally different camps. On one side, there are prokaryotes, simple bacteria. Their structure is basic, just a tiny sac of fluid with genetic material floating freely inside. They have no complex internal parts. Bacteria popped up on Earth about 4 billion years ago and remained the sole rulers of the planet for a massive chunk of time. But then, about 2 billion years ago, something unimaginable happens in the geological record. Suddenly, as if by a wave of a magic wand, eukaryotes appear. Complex biological cells that make up fungi, plants, animals, and of course you and me. Compared to a bacterium, a complex biological cell is like a modern metropolis compared to a lone tent in the woods. Inside our biological cell is a nucleus, a highly protected vault for genetic information, like a library. It has a complex highway system for transport, and most importantly, it has specialized power plants that generate energy to keep it alive. In animal cells, these power plants are called mitochondria, and in plants, the same role is played by chloroplasts, which capture sunlight. An epic question arose. How exactly did a simple bacterium manage to turn into this incredibly complex metropolis? According to classic teaching, the bacterium should have gradually, step by step, over millions of generations, complicated its structure, slowly forming a nucleus and power plants inside itself. But no one was finding any missing links. The gap between a simple bacterium and a complex biological cell was so colossal that it seemed like an unsolvable paradox. In 1967, a young researcher named Lynn Margulis proposes a completely different, radical explanation. She puts forward the theory of endosymbiosis. The word endosymbiosis comes from Greek and literally means living together inside. Margulis declared that the complex biological cell arose not through slow, random mutations, but as the result of a sudden, epic merger of completely different organisms. She paid close attention to mitochondria, those tiny power plants inside us that churn out ATP molecules, which act as the universal fuel for all biological processes. Margulis noticed something weird. Mitochondria looked exactly like independent bacteria. They had a similar shape, similar size. Moreover, mitochondria reproduced inside the biological cell completely independently of its nucleus. When a biological cell decides to divide, the mitochondria divide on their own, just pinching themselves in half like regular microbes in a puddle of water do. Lynn Margulis draws a mind-blowing conclusion. Mitochondria are ancient bacteria. Billions of years ago, a large but clumsy and low-energy bacterium tried to swallow another, smaller, but incredibly efficient bacterium that knew how to use oxygen to crank out massive amounts of energy. But by some lucky fluke, the predator couldn't digest its prey. The prey stayed alive inside the aggressor. Let's use a simple analogy from the business world to understand how genius this deal of nature was. Picture two competing corporations. One is huge. It has lots of factory space and great security, but it suffers from a chronic power shortage. The other company is a tiny startup that invented a genius portable power generator. But the startup is totally defenseless against hostile takeovers. Instead of destroying each other on the market, they decide on a full merger. The little startup moves inside the giant factory. Now the big corporation provides perfect security, a steady supply of raw materials, and safe working conditions. In return, the former startup, now an internal department, supplies this entire massive complex with clean energy 24/7. This, according to Margulis, is exactly what happened at the dawn of evolution. It was a mutually beneficial partnership that forever changed the face of the planet. Without this symbiosis, life on Earth would have stayed at the level of microscopic slime floating in a primordial ocean. No complex life forms, no giant sequoias, no dinosaurs, no humans capable of writing symphonies and flying into space would have ever appeared. You'd think Lynn Margulis's theory was incredibly beautiful and elegant, but when she tried to publish her ideas, she slammed into a brick wall of academic conservatism. Her original scientific paper was rejected 15 times in a row by different scientific journals. The leading evolutionary biologists of the time went ballistic. What do you mean? Evolution is a struggle, it's competition, it's survival of the fittest. The idea that the main driver of life's complexity wasn't a bloody battle, but peaceful cooperation and merging seemed like outrageous heresy to neo-Darwinians. Margulis was accused of building sci-fi castles in the sky based on simple visual similarities. She was openly mocked, and her ideas were called fairy tales about microbe friendship. Margulis had to endure years of intellectual isolation and ridicule. But science has one magnificent trait. Sooner or later, technology reaches a level where controversial questions can be settled with undeniable facts. That moment arrived in the late 70s and early 80s, when scientists learned how to read the genetic code of living things. Biologists extracted genetic material straight from mitochondria and subjected it to rigorous analysis. The results of this analysis hit like a bombshell and shut up the most furious critics. It turned out that mitochondria have their own separate genetic code. This code is drastically different from the genetic text stored in the central nucleus of a human biological cell. Furthermore, the shape of this genetic material was circular, exactly the same as in ancient free-living bacteria. The genetic analysis irrefutably proved, right now, descendants of ancient microorganisms are living inside every single one of our biological cells. They kept their own separate biological identity. They live, breathe, and divide inside us. They are so independent that mitochondrial genetic info is passed down strictly through the maternal line, from mother to child, without ever mixing with the father's genes. This discovery completely flipped our understanding of biology. It forced the scientific world to admit that Darwin only painted part of the picture. Competition is indeed important, but the greatest leaps in the history of life happen through cooperation. Lynn Margulis, once despised by the academic community, became a recognized giant of science. Her theory of endosymbiosis made it into every high school and college textbook worldwide. But the most amazing part of this story is the philosophical takeaway it leaves us with. Think about it. We are used to seeing ourselves as single, unified individuals. I am me. My body belongs to me. But from the perspective of cell biology, that's an illusion. Every one of us is not a single organism. We are walking colonies, giant co-ops made of trillions of ancient creatures that signed a non-aggression pact a long time ago. Every beat of your heart, every flex of a muscle, every thought in your brain right now is powered by those exact immigrant bacteria living inside you. We are literally made of tamed aliens. And this realization makes the mechanics of life far deeper, stranger, and more beautiful than any sci-fi story. When we look at the night sky, we see thousands of glowing dots. For centuries, people thought stars were unchanging. But in the early 20th century, thanks to advancements in physics, scientists finally figured out exactly how these celestial bodies work and why they shine in the first place. A star is a giant ball of gas, inside of which a colossal, non-stop battle between two mighty forces takes place. On one side is gravity. The star's own massive weight constantly tries to crush it, squeeze it under its own mass, and pull all the matter into a tiny dot in the center. On the other side is thermonuclear fusion. Right in the heart of the star, at millions of degrees, hydrogen atoms fuse together to form helium. This process pumps out an unbelievable amount of energy. It's an ongoing nuclear explosion pushing outward. The radiation from this explosion pushes against the outer layers of gas, keeping the star from collapsing. And as long as the star has hydrogen fuel, these two forces are in perfect balance. But astronomers had one logical question on their minds. What happens when the fuel runs out? The thermonuclear fire will eventually die, and the force blowing the star up from the inside will vanish. Gravity will be left as the sole winner and will start ruthlessly crushing the cooling star. By the 1920s, astrophysicists already had an answer to this question. They had discovered what are known as white dwarfs. According to their calculations, when a small star, like our Sun, burns through its energy reserves, it sheds its outer shell, and its core shrinks down to the size of a normal planet, like Earth. But the mass of this planet remains colossal. As a result, the matter inside a white dwarf is squeezed so tightly that a single cubic centimeter of this stuff weighs a whole ton. So why doesn't a white dwarf keep shrinking? Physicists explain this using a new, recently discovered phenomenon from quantum mechanics: electron degeneracy pressure. To understand this complex term, let's use a thought experiment. Imagine a huge concert hall where the audience bought tickets for specific assigned seats. The audience members are electrons. According to a strict rule of the quantum world, known as the Pauli exclusion principle, two audience members cannot sit in the exact same chair. When gravity starts crushing the star, it's the equivalent of the concert hall walls rapidly closing in, wiping out rows of seats. The audience has to take up all the remaining empty seats, packing in tighter and tighter. At some point, all the available seats in the hall are taken. The people are squeezed so hard, they start physically fighting back, bracing their shoulders and pushing against the encroaching walls. This incredible pushback from electrons that have nowhere left to squeeze into is called degeneracy pressure. It is so powerful that it can permanently halt the gravitational collapse. The star turns into a stable, dense, white dwarf and peacefully cools off for eternity. The scientific community was sure this was the universal and only finale for any star in the universe. Nature couldn't create anything more extreme. But in 1930, an event happens that changes the history of science forever. A 19-year-old Indian student named Subrahmanyan Chandrasekhar sets off on a long sea voyage on a ship from India to England to continue his studies at Cambridge. The trip took many weeks. There was no entertainment on board, and the young man amused himself by doing complex math in a notebook. Chandrasekhar decided to see what would happen if the star wasn't as small as the Sun, but several times more massive. He took the quantum mechanics equations describing electron pushback and, for the first time in history, merged them with Albert Einstein's equations of special relativity. Chandrasekhar's logic was flawless. He reasoned, the more massive the star, the harder gravity crushes the electrons. To fight this pressure, the electrons have to move faster and faster. In massive stars, electrons have to accelerate to speeds close to the speed of light. But according to Einstein, when an object approaches the speed of light, its mass starts shooting up. Chandrasekhar found a fatal mathematical paradox in his formulas. When the electrons get heavier because of their near-light speed, the gravitational pull between them gets even stronger. It creates a vicious cycle. The electrons push back, accelerate, get heavier, and gravity crushes them twice as hard. The young physicist calculated a strict mathematical limit. If the core of a dying star weighs more than 1.4 times the mass of the Sun, the quantum pushback of the electrons will inevitably be broken. Gravity will win, finally and irrevocably. But what does that mean then? What happens to the star if no known force of nature can stop its collapse? Chandrasekhar's calculations showed something unimaginable. The star will start falling into itself. It will shrink to a ball the size of a city, then the size of a football field, then the size of a grain of sand, and eventually, its entire colossal mass will vanish into a mathematical point with zero volume and infinite density. Gravity will become so unbelievable that not even light will be able to escape its grip. Chandrasekhar mathematically predicted the existence of black holes. When the young researcher arrived in England and showed his math to esteemed professors, he expected scientific triumph. But instead, he ran into an icy wall of misunderstanding and arrogance. In 1935, at a meeting of the Royal Astronomical Society in London, Chandrasekhar presented his work. Arthur Eddington, the most famous and influential astrophysicist of the era, was in the room. Eddington was the one who had experimentally confirmed Einstein's theory of relativity during a solar eclipse. Eddington's word was law. After the young Indian's presentation, Eddington took the stage and publicly trashed his work. He declared that the idea of a star shrinking into nothing was absurd. Eddington mocked Chandrasekhar's math, delivering the famous line, "There should be a law of nature to prevent a star from behaving in this absurd way." Eddington's authority was so absolute that the entire scientific community obediently agreed with him. The idea of a collapsing star was written off as a mathematical curiosity with no bearing on reality. Chandrasekhar was deeply hurt. He dropped his research in this area, left England, and went to work in the United States, deciding to never argue with Eddington again. For decades, the academic world believed that massive stars somehow magically lost their excess mass before dying to avoid a catastrophic collapse. It wasn't until 1939 that physicists Robert Oppenheimer and Hartland Snyder, using general relativity, proved Chandrasekhar was absolutely right. The collapse really is inevitable. A region of space is formed that is cut off from the rest of the universe, which would later be named a black hole. Today, the Chandrasekhar limit is one of the cornerstones of modern astrophysics. It explains the most powerful explosions in the universe. If a white dwarf in a binary star system slowly siphons gas from its neighbor star, its mass steadily grows. The exact moment its mass hits that magic limit of 1.4 solar masses, a thermonuclear catastrophe of epic proportions happens. The white dwarf explodes as a specific type of supernova, shining brighter than an entire galaxy. Astronomers use these exact explosions today as cosmic beacons to measure distances in the universe and study its expansion. And in 2019, humanity got the clearest visual proof of what that young Indian student predicted on the deck of a steamship. The Event Horizon Telescope project, which linked radio telescopes across the globe into a single Earth-sized network, managed to peer right into the center of the distant galaxy Messier 87. Scientists photographed the shadow of a supermassive black hole, the very object Arthur Eddington considered nonsense and a mistake of nature. Subrahmanyan Chandrasekhar lived to see worldwide recognition. In 1983, almost 50 years after his discovery, he won the Nobel Prize in Physics. His story is a brilliant illustration of how math can see further than human intuition. The human mind might refuse to believe the unimaginable, and authorities might try to forbid nature from acting weirdly. But formulas, if they are correct, inevitably pave the way to the truth, even if that truth hides in impenetrable darkness. Throughout the entire 20th century, stomach ulcers were a genuine curse on humanity. It was an exhausting, painful, and extremely dangerous disease that plagued millions of people worldwide. If you went to a gastroenterologist in the 70s and asked what caused this disease, you would get a totally confident, standardized answer. Medicine at the time firmly knew that ulcers were caused by poor lifestyle choices. The main culprits were considered to be stress at work, spicy food, smoking, and the overproduction of stomach acid. The logic was flawless. Stomach acid is made of concentrated hydrochloric acid. Its acidity is so high, it can dissolve a metal paperclip or a razor blade in a few days. Scientists believe that under nervous tension, the stomach started pumping out too much of this acid, which then simply ate away at the organ's own walls. The treatment naturally flowed from this logic. Patients were prescribed strict, tasteless diets, forced to drink gallons of milk to soothe their stomachs, advised to switch to less stressful jobs, and prescribed tons of acid-reducing meds. If none of that worked, the only radical way out was surgery, where a doctor simply sliced off the damaged part of the patient's stomach. There was a fundamental medical dogma that no sane professor ever questioned. The stomach is an absolutely sterile environment. It was believed that no microorganism could survive in such a harsh, acidic ocean. Any bacteria that got into the stomach with food would die in seconds. Period. It was the law. In 1979, an Australian pathologist named Robin Warren was sitting at his microscope, examining tissue samples taken from the stomachs of patients with chronic gastritis and ulcers. And he noticed something completely impossible. Right there in the mucous membrane of the inflamed areas, he saw tiny, spiral-shaped bacteria. They weren't just hanging out. They were living, thriving, and multiplying in huge numbers. Warren showed his slides to colleagues, but they just brushed him off. They told him it was just standard sample contamination. The bacteria, they said, got on the glass because the tools weren't sterilized properly. Life can't exist in acid. But Warren didn't give up. In 1981, a young and incredibly stubborn medical intern named Barry Marshall joined his research. Together, they started systematically studying patients and found that these spiral microbes were present in almost 100% of ulcer patients. The researchers named this bacterium Helicobacter pylori. Marshall and Warren put forward a revolutionary hypothesis. Stomach ulcers aren't caused by stress or spicy food. They are caused by an infection. And that means this awful disease shouldn't be treated with a surgeon's scalpel, but with a cheap standard course of antibiotics. When they presented their findings at gastroenterology conferences, the medical community's reaction ranged from patronizing smiles to outright outrage. Respected professors, who had built stellar careers studying the psychosomatic causes of ulcers and surgical ways to treat them, refused to even listen to two unknown doctors from Australia. Pharma giants making billions selling acid-reducing pills also showed zero interest in the idea that the disease could be cured permanently with cheap antibiotics. The critics' main argument was always the same. How can a bacterium survive in hydrochloric acid? It breaks the laws of chemistry. Marshall and Warren had to find the answer to this question to prove they were right, and they figured out the survival mechanism of this microbe, which turned out to be truly genius. Let's break this down. Picture a diver who has to plunge into a vat of corrosive acid. To survive, the diver puts on a special suit that constantly sprays a cloud of alkaline neutralizer all around him. When the acid hits this cloud, it turns into harmless water, and the diver stays perfectly safe. The Helicobacter pylori bacterium does something very similar. It secretes a specific enzyme called urease. This enzyme reacts chemically with urea, which is always present in the stomach, breaking it down and releasing ammonia. Ammonia is highly alkaline. The bacterium literally wraps itself in a dense ammonia shield. Inside this microscopic protective bubble, the acidity drops to comfortable levels. The bacterium calmly uses its spiral-shaped tail to drill through the stomach's protective mucus layer, latches onto the epithelial cells and starts pumping out toxins, causing inflammation and eventually an ulcer. The mechanism was uncovered. The link was established. But critics kept demanding bulletproof evidence. In science, there is a strict standard called Koch's postulates. To prove that a specific bacterium causes a specific disease, you have to grow the bacteria in a lab, infect a healthy animal with it, wait for symptoms to develop, and then isolate the same bacteria from the sick animal. And here, Marshall hit an unbeatable roadblock. Helicobacter pylori refused to infect lab mice, rats, or pigs. Over the course of evolution, this microbe adapted exclusively to the human body. Doctors don't have the right to intentionally infect healthy humans with dangerous infections. It's a strict violation of medical ethics. The research hit a dead end. Marshall knew millions of people were continuing to suffer and go under the knife just because the academic elite was too stubborn. And then, in 1984, Barry Marshall makes a decision that permanently writes his name into the pantheon of the craziest and most heroic scientists in medical history. He decides to run the experiment on himself. Marshall underwent an endoscopy, which confirmed his stomach was perfectly healthy and showed no signs of inflammation or bacteria. Then he went into the lab, grabbed a beaker of warm meat broth swirling with billions of lab-grown Helicobacter pylori bacteria taken from a sick patient's stomach. Marshall chugged this murky, dangerous liquid in one gulp. He didn't tell anyone about his plan, not even his own wife. Marshall expected symptoms to show up in a few years, since ulcers were considered a slow-developing disease. But nature had other plans. Just 3 days later, he was hit with severe nausea. He was throwing up in the mornings and feeling awful stomach pain. His mom and wife noticed his breath smelled terrible. Remember the bacterium's ammonia shield? That exact ammonia, pumped out by billions of microbes in his stomach, was causing the sharp smell. 10 days later, Marshall went in for another endoscopy. The results were stunning. His once healthy stomach was crimson from severe inflammation. He had developed acute gastritis, the precursor to an ulcer. And everywhere, crawling in every square millimeter of the inflamed tissue, were those spiral bacteria. Koch's postulates were fulfilled. Marshall proved that the infection was the root cause of the disease. Right after that, he started a course of antibiotics and completely cured himself in 2 weeks. When Marshall published the results of this extreme experiment, the medical community was shocked. They couldn't ignore the paper anymore. Massive clinical trials kicked off all over the world. Doctors were amazed to find that a short course of antibiotic pills and a drug that temporarily lowers stomach acid to help the meds work cured 90% of patients permanently. Surgeries to chop out parts of the stomach became a thing of the past. In 1994, the U.S. National Institutes of Health officially recognized Helicobacter pylori as the main cause of ulcer disease. And in 2005, Barry Marshall and Robin Warren won the Nobel Prize in Physiology or Medicine. Their discovery, won at the cost of unbelievable personal courage and pushing back against the entire scientific establishment, saved hundreds of millions of people from unbearable pain and brutal surgeries. This story clearly demonstrates one important thing. In science, there are no absolute dogmas. The authority of textbooks, the confidence of professors, and century-old traditions mean absolutely nothing if they contradict real facts. And sometimes, to smash a wall of ignorance, it takes not just a sharp mind, but a touch of genuine, reckless madness. I wonder how many other medical truths we swear by right now will turn out to be just convenient misconceptions waiting for their own Barry Marshall. Let's imagine how mid-20th century biology viewed the makeup of any living organism. After James Watson and Francis Crick deciphered the structure of the DNA molecule in 1953, an incredibly clear and strict paradigm took hold in science. Scientists started looking at the genetic code as a fundamental, unshakable architectural blueprint. Under this paradigm, DNA was seen as a giant library, where every book is a chromosome, and every page in that book is an individual gene. The main rule of this library was absolute stability. It was believed that genes sat in their places as immovably as letters printed on paper. This stability guaranteed that offspring would look like their parents. Changes, of course, did happen, but they were viewed as extremely rare, random typos in the copying process, mutations. This concept of a static genome was so solid and logical that no one in their right mind tried to question it. It's against the backdrop of this monumental scientific certainty that Barbara McClintock's story unfolds. She was a geneticist, a woman of incredible intellect and phenomenal observational skills. Unlike many of her colleagues, who were increasingly switching to studying simple bacteria and viruses to understand the basic mechanics of heredity, McClintock dedicated her life to studying corn. She worked at the Cold Spring Harbor Laboratory, spending endless hours in cornfields and then meticulously studying the cobs and chromosomes under a microscope. Corn was the perfect subject for her. If you've ever seen decorative Indian corn, you've probably noticed its kernels. They can be yellow, red, purple, and these colors are often mixed on a single cob, and sometimes weird spots and stripes appear on a single kernel. To a regular person, it's just a pretty pattern of nature. But to Barbara McClintock, these colored spots were a coded message, a key to understanding how genes work. In the late 1940s, a few years before the double helix was discovered, McClintock started noticing something completely illogical in her experiments. She was crossbreeding certain types of corn and noticed that changes in kernel color were happening way too often and way too unpredictably to be explained by random classic mutations. Studying the chromosomes of these plants under a microscope, she discovered a paradox. Certain chunks of genetic material literally vanished from their usual spot on one chromosome and mystically reappeared on another. She came to a conclusion that tore down all the foundations of the science of the time. The genome is not a static book. Inside it, there are special, mobile elements, genes that can cut themselves out of the DNA chain and paste themselves into entirely new spots. McClintock called them controlling elements, and today, science uses the term transposons. Let's break this mechanism down through a detailed mental analogy to understand the true depth of her discovery. Imagine a massive, thick encyclopedia containing instructions for building and running a complex factory. All the pages are numbered, and all the paragraphs follow each other in strict order. Suddenly, one of the paragraphs, as if acting on its own will, detaches from the page, flies 300 pages forward, and pastes itself right in the middle of a sentence describing how the main conveyor belt works. What happens? The manual becomes unreadable right there. The conveyor belt stops or starts glitching. This is exactly what McClintock observed in corn. If a jumping gene landed right inside the gene responsible for making purple pigment, that pigment gene broke, stopped working, and the kernel grew incolorless, meaning yellow. But the most mind-blowing part came next. Since this element stayed mobile, in the next generation of cells, it could jump right back out just as suddenly. As soon as it left the pigment gene, the instruction manual was restored, and the cells started making purple paint again. This is exactly why purple spots appeared on yellow kernels. In some cells, the gene was turned off by the jumping element, but in other cells, the element had already jumped somewhere else, turning the color back on. McClintock realized the genome is a dynamic, living, constantly changing system. It's not just a data archive. It's a highly complex machine that can edit itself, rewire itself, and react to external stress by shuffling blocks of info around. In 1951, Barbara McClintock decided to present her staggering findings at a prestigious scientific symposium. She prepared a highly detailed report, laying out the theory of mobile genetic elements step by step, backing it up with hard data and photos of chromosomes. The reaction of the academic community was ice cold. A dead silence hung over the room. No one asked questions. No one started a debate. Her ideas were so alien to the accepted paradigm of a static genome that the best minds in biology simply couldn't digest them. As McClintock herself recalled, her colleagues looked at her like she had lost her mind. Her mathematical precision and flawless logic were ignored because they demanded a total rewrite of everything genetics believed in. The male-dominated conservative world of science wasn't ready to accept the idea that genes could behave so chaotically, especially coming from a woman studying colored corn. After this presentation, McClintock hit a wall of misunderstanding. Respected scientists thought her work was too convoluted and irrelevant to real science. At a certain point, tired of being mocked and ignored, she stopped publishing papers on mobile elements. She just kept working alone, absolutely certain she was right. "When you know you are right," she later said, "you don't care what others think. You just wait for them to catch up." It took the academic world almost 30 years to catch up to Barbara McClintock. In the late 60s and early 70s, molecular biologists, armed with powerful new tools for decoding DNA, started finding mobile elements in bacteria. Then they found them in yeast, then in fruit flies. And every time scientists found these migrating snippets of genetic code, they were amazed to realize their mechanics had been perfectly described by a lone corn researcher decades earlier. By the 80s, it became crystal clear that transposons weren't some weird plant anomaly, but a fundamental property of all life on Earth. And the scale of this phenomenon turned out to be truly colossal. Tying this back to modern reality forces us to rethink our own nature. The Human Genome Project revealed an incredible fact. Almost half, about 45%, of all our DNA is made up of mobile genetic elements. Half of the instruction manual that builds our body consists of genetic drifters that have been cutting and pasting themselves, hopping around our chromosomes over millions of years of evolution. Today we know these jumping genes played a critical role in our development. They acted as engines of evolution, shuffling genetic material, creating new combos, and letting organisms rapidly adapt to changing environments. Crucial functions of our bodies, including how our immune system works and the development of the placenta, only became possible thanks to ancient jumping genes that inserted themselves into the right spots in our genetic code a long time ago. In 1983, when Barbara McClintock was 81 years old, the Royal Swedish Academy of Sciences finally recognized her genius. She became the first woman in history to win an unshared Nobel Prize in physiology or medicine. The story of Barbara McClintock is the triumph of pure, unbiased observation over dogmatic thinking. It's the story of how one woman, looking closely at multicolored kernels in a farm field, managed to see what was hidden right in the heart of all living things. She proved that nature is never static. Our genome is not a law carved in stone. It is a noisy, restless, constantly edited book whose pages are still being rewritten right now in every cell of our body. For a long time, the mystery of the dinosaur extinction was one of the most romanticized and yet most tangled problems in science. For almost 150 years, paleontology stood on the solid foundation of a philosophical concept called uniformitarianism. This concept claimed that all changes on our planet happen extremely slowly, gradually, step by step, as a result of the exact same normal processes we see outside our windows today. Erosion, wind, tides, gradual climate shifts. These, according to academic science, were what shaped Earth's history over billions of years. Within this smooth, unhurried worldview, any sudden catastrophes were considered anti-scientific heresy, leftovers of biblical tales about a global flood. Therefore, scientists explained the disappearance of the dinosaurs, giant reptiles that completely dominated the planet for almost 160 million years, using nothing but slow processes. There were dozens of theories. Some professors argued the climate gradually got too cold, and cold-blooded animals just couldn't adapt. Others guessed that new plant species were toxic to them. There was even a popular theory that tiny, quick mammals slowly ate all the dinosaur eggs. The core of all these hypotheses boiled down to one thing. Dinosaurs just became obsolete, lost the evolutionary race, and quietly faded away over millions of years, making way for more advanced creatures. But in the late 1970s, this calm, orderly view of the world was smashed to pieces. And it was smashed by a man who had absolutely nothing to do with paleontology. His name was Luis Alvarez. He was a brilliant nuclear physicist, a Nobel laureate, a guy who helped invent radar and worked on the atomic bomb. The story started when Luis's son, geologist Walter Alvarez, was working in the mountains of Italy near the town of Gubbio. He was studying ancient limestone deposits. Looking closely at the cliffs, Walter found a very weird anomaly. In a layer of rock dating back roughly 66 million years, there was a thin strip of gray clay, just a centimeter thick. Below this strip, the limestone was literally packed with the fossilized shells of microscopic marine organisms, and right above it, in the younger layers, those organisms practically vanished. This thin line of clay was basically the border between life and death. In geology, it's called the KPG boundary. Walter brought samples of this clay to his dad. Luis Alvarez, the physicist, was hooked by one question. How long did it take this 1 centimeter layer to form? To measure the time, he decided to look for cosmic dust in the samples. Earth is constantly bombarded by micrometeorites that slowly but steadily settle on the surface. Alvarez figured, by measuring the concentration of certain rare elements specific to cosmic dust, you could calculate exactly how many thousands of years it took for that centimeter of clay to pile up. The scientists picked the chemical element iridium for their search. Iridium is a heavy metal. During Earth's formation, when our planet was a ball of molten magma, almost all of Earth's iridium sank deep into the core, so it's incredibly rare in the Earth's crust. But in meteorites and asteroids, its concentration is still huge. Luis Alvarez sent the samples to the lab for analysis, expecting to see vanishingly small traces of this element. But the results left the physicists stunned. The iridium levels in the thin clay layer were 300 times higher than normal. You couldn't explain that with the slow settling of cosmic dust. Such a colossal concentration meant only one thing. 66 million years ago, a massive amount of extraterrestrial material slammed into Earth, and it all hit at once. In 1980, Luis and Walter Alvarez published a paper putting forward a totally insane, radical hypothesis. They declared there was no slow extinction. One terrible day, a giant asteroid at least 10 kilometers across smashed into our planet. This space rock hit the Earth's surface at a speed of about 20 kilometers per second. Let's break down the physics of this unthinkable event. When a rock the size of Mount Everest slams into a planet, the energy of the explosion is greater than 1 billion atomic bombs. At the impact site, the temperature instantly hits tens of thousands of degrees, vaporizing not just the asteroid itself, but thousands of cubic kilometers of Earth's rock. A massive amount of superheated steam, melted rock, and ash is blasted into the atmosphere. This ejected debris flies on ballistic trajectories, reaches near space, and then starts falling back to Earth, superheating from friction with the air. The sky across the whole planet starts glowing red hot, acting like a giant broiler. The surface of the continents catches fire, triggering global wildfires that wipe out any living thing that couldn't hide underground or in the water. But the worst part comes later. The ash from the fires, the soot, and the kicked-up dust form a thick, impenetrable cloud that completely wraps around the globe. Using his physics background, Alvarez compared this phenomenon to nuclear winter. Sunlight can no longer reach the surface. The planet is plunged into pitch blackness that lasts for years. Without sunlight, global photosynthesis shuts down. The plants die. Then the huge herbivores die, out of food. And after them, the carnivorous reptiles die out too. The whole food chain collapses like a house of cards. The only things that survived this pitch blackness were small creatures that ate carrion and seeds and could hide in burrows, our distant mammalian ancestors. You'd think the theory was backed by solid math and chemistry, but the academic community reacted with an explosion of outrage. Paleontologists were just furious. They saw Alvarez's hypothesis as an arrogant invasion by physicists into their field. Prominent professors openly mocked the asteroid idea. They said it sounded like the plot of a cheap Hollywood movie, not real science. Physicists sticking their noses where they don't belong with their math toys, scientific journals wrote. The critics' main argument was devastating. If a 10-kilometer asteroid hit Earth, where is the crater? An impact of that unbelievable force should have left a colossal crater almost 200 kilometers across. You can't just lose a hole that big on the surface of a planet. But Alvarez couldn't point to the impact site. It became his weakest link. Luis Alvarez died in 1988, never living to see the moment he was definitively proven right. But the proof was already lying under thick layers of geological rock, waiting for its moment. In the early 90s, researchers noticed weird geological anomalies on the Yucatan Peninsula in Mexico. Back in the 70s, the Mexican State Oil Company had run drilling and gravity measurements there. They found a giant circular structure hidden under ice and limestone, but the oil guys didn't care about dinosaurs. They were looking for oil, so the data just gathered dust in the archives. When geologists finally got their hands on this data and ran new tests, they found exactly what Alvarez's theory predicted. Buried under a kilometer-thick layer of limestone was a crater 180 kilometers across. They named it Chicxulub, after a nearby village. In the rocks of this crater they found shocked quartz and tektites, tiny drops of glass that only form under extreme pressure and heat, conditions strictly unique to giant cosmic impacts or nuclear explosions. On top of that, radioisotope dating of the rocks showed the impact happened at the exact boundary of the dinosaur extinction, give or take a few tens of thousands of years. A microscopic margin of error on a geological scale. The academic world surrendered. The iridium anomaly found in Italy turned out to be just a thin layer of dust that settled all over the planet after the Mexican catastrophe. Today, the asteroid theory of the dinosaur extinction isn't just accepted, it's part of the school curriculum. But the philosophical fallout from this discovery was even bigger than the paleontological investigation itself. Alvarez's discovery forced us to totally rethink our understanding of evolution. We're used to thinking the strongest, smartest, and fittest survive. But the Chicxulub asteroid impact proves that cosmic luck plays a massive, deciding role in evolution. The dinosaurs weren't a dead-end branch. They were perfectly adapted to their world. They were thriving and evolving. They died, not because they were worse, but simply because they were catastrophically unlucky to be in the path of a giant rock. And we humans exist today only because, 66 million years ago, our tiny, fluffy ancestors happened to be small enough to hide in the mud and survive a nuclear winter. This story reminds us of how fragile life on Earth is, and how much our fate depends on the silent void of space. To grasp the scale of the shock caused by the next discovery, we need to dive deep into what's called the central dogma of molecular biology. This dogma was formulated in the mid-20th century, and it became a kind of constitution for all scientists studying life. The rule was simple, universal, and absolutely unbreakable. Genetic information only ever flows in one direction. It is stored in DNA, then transcribed into RNA, and that, in turn, serves as the instruction manual for making proteins, the very building blocks our bodies are made of. From this fundamental law came a rule concerning any infectious disease. Medicine firmly knew that any pathogen, whether it's a giant parasitic worm, a fungus, a lethal bacterium, or a tiny virus, must have genetic material. To multiply and infect new cells, the infectious agent has to bring its own instructions, its own DNA or RNA. An infection without genes was considered absolute nonsense. It was as ridiculous as imagining a book with no letters in it that somehow manages to copy itself. This is the exact ironclad rule American neurologist Stanley Prusiner ran into in the 1970s. His work began with an in-depth study of a group of incredibly weird and terrifying brain diseases. One of these diseases was scrapie in sheep. Infected sheep would act completely crazy, constantly scrape against fences, lose their coordination, and eventually die. Another was kuru, a lethal disease that hit Papuan tribes in New Guinea because of their ritual cannibalism. And humans got a rare, incurable illness called Creutzfeldt-Jakob disease, which turned the human brain into a porous sponge, stripping the patient of their mind and life. Scientists knew all these diseases were contagious. Researchers successfully transmitted them from one animal to another in the lab. It made logical sense to assume the culprit was some kind of slow virus that hides in the body for a long time before wrecking the nervous system. Labs all over the world spent millions of dollars trying to track down this hypothetical virus, trying to find its genetic code. But the experiment results had biologists baffled. This mysterious infectious agent acted like an unkillable monster. Scientists hit samples of infected brain tissue with colossal doses of radiation, blasted them with UV light, boiled them, treated them with formaldehyde. Any normal virus or bacteria would instantly fall apart from that kind of abuse, because radiation and chemicals tear nucleic acid chains to shreds. But this pathogen stayed active and deadly. It was as if it was laughing at the laws of biology. Stanley Prusiner decided to tackle the problem from a different angle. For an entire decade, he painstakingly purified extracts from the brains of infected hamsters. He used highly complex chemical procedures, centrifuges, and enzymes to filter out all known components step by step. He destroyed all the nucleic acids, destroyed all the sugars, destroyed the lipids. In 1982, Prusiner published his results. He declared that in the purified sample, which was still capable of causing a 100% lethal infection, not a single molecule of DNA was left. There was no genetic material there. The infectious agent turned out to be a regular lone protein. Prusiner coined a new name for it, prion, mashing up the words protein and infection. Prusiner's claim hit like a bolt from the blue. It contradicted everything biologists had been taught in school. How can a piece of protein, with 0 reproductive instructions inside it, cause an infection? How does it copy itself? To explain this paradox, Prusiner proposed a revolutionary mechanism that forces us to look at proteins in a totally new way. We're used to thinking of proteins as chemical formulas. But in reality, a protein is a complex 3D structure. Imagine a long wire that is crumpled, folded, and tied into knots in an incredibly complex way to give it a specific shape. This exact 3D shape dictates how the protein will work in the body. Normal prion protein is found in every mammal, humans included, and works peacefully in our nerve cells. But sometimes, a catastrophic glitch happens. The normal protein molecule suddenly changes its 3D structure. It folds incorrectly. Let's use an analogy. Imagine a normal rain umbrella. That's the normal protein. It does its job perfectly. Now imagine a strong gust of wind blows it inside out, breaking the spokes. The umbrella lost its useful function. This is the disease-causing prion. But the scariest and most mystical part of Prusiner's theory was this. When this broken, inside-out umbrella bumps into a regular, normal umbrella, it somehow acts as a physical template. It forces the normal umbrella to flip inside out too. A chain reaction starts. 1 broken protein makes 2, 2 make 4, 4 make 8. These misfolded, insoluble proteins start clumping together into huge plaques inside brain cells. The cells can't handle the buildup of this trash. They burst and die, leaving empty, microscopic holes behind. The brain literally turns into a sponge full of holes. The scientific community's reaction to Prusiner's paper was furious and merciless. He was accused of ignorance, of being a fraud, and they claimed his samples just weren't purified well enough and a tiny virus was hiding in there somewhere. Virologists published scathing articles calling the idea of a replicating protein scientific heresy. Leading scientific journals refused to publish his work for years. Prusiner became an outcast who was openly mocked at science conferences. The idea of an infection without genes attacked the holy of holies of molecular biology, and the academic inquisition was ready to tear the scientist apart. Prusiner recalled that this period was the hardest of his life. He kept working in an atmosphere of total distrust, trying to gather more evidence. And the grim proof that he was right came from a totally unexpected place, in the form of a massive tragedy. In the late 80s and early 90s, an unprecedented epidemic of mad cow disease broke out in the UK. Hundreds of thousands of cows started losing control of their bodies, got aggressive, and died. It turned out that farmers, trying to boost milk yields, were adding cheap meat and bone meal to the cow's feed, made from the remains of sheep infected with scrapie. The infectious agent survived the industrial heat treatment and ended up in the cows' stomachs. But the worst part happened later, when humans who ate the infected beef started coming down with a new, highly aggressive variant of Creutzfeldt-Jakob disease en masse. Governments and health ministries panicked. The old virology methods were useless against this invisible enemy. And that's when the global scientific community was forced to turn to the rejected Prusiner. His prion theory perfectly, down to the smallest detail, described everything that was happening. Prions, having no nucleic acids, weren't destroyed when meat was fried or boiled. Once in the human body, they made their way to the brain and kicked off that exact umbrella-flipping chain reaction, turning normal human proteins into lethal clumps. Under the pressure of undeniable facts and a public health crisis, the academic world was forced to admit defeat. The central dogma of biology wasn't canceled, but it had to take a massive radical amendment. Nature turned out to be far more inventive and dangerous than scientists thought. Proteins really can transmit info and cause infectious diseases using pure geometric influence instead of a genetic code. In 1997, Stanley Prusiner, the man who had been called a crazy heretic for over a decade, walked onto the stage in Stockholm to accept the Nobel Prize in Physiology or Medicine. Like Barbara McClintock, he won the award unshared, which is super rare in modern science and highlights the sheer scale of his individual genius. Today, the prion concept doesn't just save us from lethal epidemics by ensuring ultra-strict meat production control. It opened a totally new field in neurology. Modern researchers believe similar protein misfolding mechanisms might be the root cause of Alzheimer's and Parkinson's diseases. The story of discovering prions leaves us with a deep sense of unease and awe at how the micro-world works. We're used to thinking we fully understand the rules of life and have things under control. But nature manages to break our most fundamental rules, hiding lethal danger not in the complex genetic codes of hostile viruses, but in the geometry of our very own native molecules that just happen to fold at the wrong angle one day. And that fact forces us to treat the mysteries still hiding inside us with immense respect and caution. The famous phrase, "nerve cells don't regenerate," is something absolutely everyone knows. For almost the entire 20th century, this statement wasn't just a common saying. It was an unbreakable, ironclad law of biology. The founder of modern neurobiology is considered to be the brilliant early 20th century researcher, Santiago Ramón y Cajal. He was the one who drew detailed sketches of the nervous system and ruled, the adult human brain is a finished, static structure. It was believed that we are born with a fixed supply of neurons, and from day one of our lives, that supply relentlessly depletes. Every drop of alcohol drunk, every stressful event, every injury only drops the nerve cell count. The brain was seen as an ultra-complex biological computer whose parts wear out over time and can never be replaced. In the 1960s, biologist Joseph Altman was working at MIT. He was studying the brains of adult rats and decided to use a totally brand new technology for the time. He injected the animals with a special radioactive substance that only built itself into newly created DNA. Meaning, this stuff could only end up inside cells that had recently been born through cell division. When Altman looked at the brain slices under a microscope, he saw something that completely contradicted the academic textbooks. In one specific area of the brain called the hippocampus, which handles memory formation, tiny radioactive markers were clearly glowing. This meant only one thing. The brain of an adult mammal was creating new nerve cells right now, in this very second. The process of neurogenesis was still happening even in adulthood. Altman published a series of brilliant, highly documented scientific papers. But the reaction from the scientific community was disheartening. His work wasn't trashed or mocked. It was just politely ignored. The authority of the old dogmas was so huge that none of the leading neurobiologists even wanted to try and replicate the young scientist's experiments. Altman's papers sank into the archives. He couldn't get funding to continue his research, and eventually, he was forced to leave the institute. Let's break down why Altman's discovery is so monumental. Let's compare our mind not to a machine, but to a dense forest. If the old dogma were true, the brain would be a forest where trees can only age, rot, and get blown over by the wind, leaving empty clearings behind. But the discovery of neurogenesis showed that fresh shoots can grow where trunks have fallen. The brain turned out to be an incredibly plastic system. Justice wasn't served until the very end of the 90s. Swedish oncologist Peter Eriksson teamed up with American neurobiologist Fred Gage. They studied tissue samples from humans who had been injected with similar chemical markers for medical reasons. The researchers definitively and irrefutably proved that the human hippocampus is capable of growing 700 to 1,000 new neurons every single day throughout our entire lives. Today we know for a fact that physical activity, learning new skills, and mental workouts literally force our brains to forge new neural connections and cells. A discovery that was once buried under a thick layer of academic conservatism gave us the most optimistic idea in medical history. We hold on to the ability to renew ourselves right up until the very last day of our lives. All of classical physics is built on one intuitive principle, the principle of locality. If you want to affect something, you have to make physical contact with that object. You can push a ball with your hand, or act on it with an invisible gravitational field. But any interaction takes time. Albert Einstein's general theory of relativity set a hard, absolute limit. Nothing in the universe, no energy, and no information can move faster than the speed of light, which is roughly 300,000 kilometers per second. But in the 1920s and 30s, quantum mechanics, the science of the micro world, started to take shape, and its mathematical equations predicted a weird glitch that completely destroyed common sense. It turned out that two particles, say two photons, could be linked together in a special way. Physicists called this quantum entanglement. To grasp the scale of this insanity, let's do a thought experiment. Imagine two magical dice. You put one die in your pocket and fly to Mars, while the second die stays on Earth. Now, if someone rolls the Earth die and gets a 6, your Martian die will instantly, without the slightest delay, also roll a 6. It happens instantaneously. There are no invisible wires, radio signals, or light beams between them. A change in the state of one particle instantly dictates the state of its partner, even if they are on opposite ends of the galaxy. Albert Einstein thought this was a fundamental mistake. He flat out refused to believe nature could act in such a ridiculous way. Einstein dismissively called quantum entanglement spooky action at a distance. He was sure quantum mechanics was just incomplete, and that the particles agreed on their states beforehand, before they ever flew apart. For decades, this debate remained purely philosophical. No one knew how to test it experimentally. But in 1964, theoretical physicist John Bell developed a genius mathematical theorem. Bell proved that you could run a strict statistical test that would settle the debate forever. If Einstein was right, the experiment results would obey certain mathematical limits. And if quantum mechanics, with its mystical instant connection, was right, those limits would be violated. For a long time, the academic world thought Bell's work had no practical use. Many journals refused to publish that kind of research, treating it more like abstract philosophy. It wasn't until 1982 that French physicist Alain Aspect managed to build an ultra-complex optical setup. He started firing entangled photons in opposite directions across the lab and tweaking the detector settings at the very last microsecond while the particles were in flight. Light simply wouldn't have enough time to pass information from one detector to the other. The measurement results were crystal clear. John Bell's limits were violated. Albert Einstein, the greatest mind of the 20th century, was wrong. Spooky action at a distance really does exist. In 2022, Alain Aspect and his colleagues won the Nobel Prize in Physics for these experiments. Our universe turned out to be a much weirder and more deeply connected place than we could have ever imagined. And today, this crazy idea is the foundation for developing quantum computers and absolutely unbreakable encryption systems. For millennia, people viewed space as a completely empty stage. Stars and planets seemed like actors playing out their roles against a backdrop of silent, motionless void. As we already figured out earlier, the general theory of relativity changed that idea forever. Space and time turned out to be a single, flexible fabric that can warp under the weight of massive objects. But another, incredibly terrifying consequence popped out of the equations. If objects in the universe move with colossal acceleration, they shouldn't just dent space. They should create literal waves in it. Just like a rock thrown into a still pond makes outward rippling circles, the collision of giant stars should send ripples through space itself across the universe. Physicists called these vibrations gravitational waves. The author of the theory himself doubted they were real for a long time. For a while, he even thought they were a mathematical artifact, a mistake in his own math. Physicists argued over whether these waves carried real energy, or were just an illusion spawned by complex formulas. The main problem was that the fabric of space-time is incredibly stiff. To make even a tiny wave, you need a catastrophe of unimaginable scale, like two black holes merging. But by the time a wave like that travels millions of light years and hits Earth, its amplitude becomes so tiny that measuring it is physically impossible. But in the 70s, a group of insanely ambitious physicists, including Kip Thorne and Rainer Weiss, decided to challenge the impossible. They proposed building the Laser Interferometer Gravitational Wave Observatory, LIGO. This project dragged on for decades, swallowed billions of dollars, and took brutal criticism from skeptics who thought it was a massive waste of money. Picture how this observatory is built. It's two giant concrete pipes, each 4 kilometers long, laid out in an L shape. A perfect vacuum is created inside the pipes. A powerful laser beam is split in half and sent traveling down these pipes, bouncing off a system of absolutely flawless mirrors. If a gravitational wave actually exists and passes through Earth, it should literally stretch space itself along one pipe and compress it along the other. Because of this, the laser beams will come back slightly out of sync with each other. Just so you understand the insanity of this task, the scientists had to measure a change in the length of a 4-kilometer pipe by an amount 10,000 times smaller than a single proton. That's the equivalent of measuring the distance from Earth to the nearest star system, Alpha Centauri, with an accuracy down to the width of a human hair. The instruments were so sensitive they picked up the noise of ocean waves hundreds of miles away from the observatory, and even trees falling in the woods. The engineers had to invent the most advanced seismic isolation systems ever made. On September 14, 2015, after decades of grueling work and failures, The detectors picked up a clear, unique signal. It lasted just 0.2 of a second. Computer analysis showed this blip exactly matched the predictions made a century earlier. The observatory had caught the ripples from the merger of two black holes, each weighing 30 times more than our sun. This catastrophe happened over 1 billion years ago. In the moment of their collision, they released energy dozens of times greater than the light of all the stars in the entire observable universe combined. And this colossal event caused a laser mirror on Earth to jiggle by a fraction of the size of an atom. In 2017, Thorne and Weiss rightfully won the Nobel Prize. This discovery marked the dawn of a totally new era in astronomy. If before we could only look at the universe using light, now we have learned to listen to it. We can literally feel the tremors of reality itself. Wrapping up our journey, I want to ask one really important question. We started with drifting continents and invisible infections, walked through the weirdness of the quantum world, and finished with the trembling of the fabric of the universe itself. Every single one of these discoveries was once considered anti-scientific heresy, the ramblings of a madman, and mathematical nonsense. Respected professors destroyed the careers of lone geniuses for daring to step outside conventional thinking. It makes you wonder, which of the crazy hypotheses that the academic world is arrogantly laughing at right now will become basic high school curriculum for our descendants? Science is not a collection of frozen dogmas. It lives, pulses, and constantly makes mistakes, only to eventually smash its way through to the truth. Are we ready to admit that the universe still hides an infinite number of mysteries, and that it will always be just a little bit smarter than us?